All right, let's go ahead and begin. So don't forget your exam. Your next one is on Tuesday. We will review for that on Monday. Okay? So yesterday we learned a little bit about amino acids. Do you remember what that central carbon is called with all your functional groups coming off of it? Alpha. It's your alpha carbon. Let's see. What are the two functional groups that come off every single amino acid? The carboxylic acid or the carboxyl, either way. And amine. What is that bond called whenever you join two amino acids together? Amide or peptide, depending on if you're in organic chemistry or biochemistry. I will accept either. What is it called when you have a positive and a negative in the same compound? Yes, zwitterionic. Okay, and then we learned two amino acids yesterday. What is the R group coming off glycine? H, and then alanine? Methyl. Or CH3, same thing. Okay, so the two we're going to learn today, the first one is proline. Now, I know this one kind of looks strange, but look at it this way. So this right here, this carbon is your alpha carbon because you find your carboxylic acid, find your amine, where they both meet, see right here, that's your alpha carbon. Now what happens with this one, which is unique, this is basically CH2, 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 but the last CH2 comes around and bonds back to nitrogen. So normally, if I come back to like alanine, see your alpha carbon, like you just have a methyl, but imagine if it just came, get like maybe another CH2 right here and it bonded also to the nitrogen. So again, this is just a CH2, CH2, CH2 bonded to itself. So it's like a propyl bonded back to nitrogen. Does that make sense? Can you kind of see it? Maybe, sort of. So if that's your alpha carbon, right? Carboxylic acid and amine. Now, your R group right here is CH2, 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 okay? Now, if I take that away, it looks a little bit more like your carboxylic acid, and it's just bonded back to the nitrogen to form a ring. So that is your proline. This one doesn't fold very well because of the ring, so it's not used in a lot of your alpha and beta structures. Those are your structures whenever you start, you'll have these long amino acid chains, and they start coming together to make these three-dimensional structures where you get your protein folding. They don't usually occur in those. These usually just occur in a single chain because they don't fold very well. Again, due to this ring here. The last one is valine. This is an isopropyl group. Remember the isopropyl at the end kind of looks like a V, right? So that's how I remember valine, because it looks like it has the V at the end. This is an essential amino acid. Anybody know what that means? Yeah, correct. So your body doesn't make this. You have to actually eat this. So you get it in your diet. You need it, part of your 20, and you have to get it through your diet. So pretty much any food that's high in protein, peanuts, meat, lentils, any of those are high in valine. So anytime you see essential, that just means you have to get that in your diet. So we have valine, which is isopropyl. Propyl meaning 3 carbons, 1, 2, 3. Iso meaning ending in this sort of V shape. And then if we come back here, proline. So on Monday we'll learn 2 more, and those will be what you're responsible for exam 3. Oh yeah. Valine. Is this PowerPoint not posted? Because I can post it if it's not. Would you? It's in like week 3? So it's in a previous week. Let me know if you can't find it or you can't open it. I'll just email it out. But then you don't have to write all this down. It's on there somewhere. Everybody good with this? Okay. Chapter 17, so let's review what we did yesterday. For what chapter? 17? Yeah, I'll do it like after the break. I'll pull it up and look at it. You can't see any of those. Just sitting here writing. There you go. Okay, on the first one there, what does that put on benzene? Bromine. What about the next one? SO3H. What about this one? Chlorine. And this one? NO2. And then the last one? It goes NO2 and then it turns NO2 into what? NH2. Any questions on those? And let's do the mechanisms for these two here. Okay, so what's the first part of this mechanism? Yeah, making NO2. Okay, so what happens here? The OH will what? Grab an H, and at the same time, it can leave and grab an H, but what makes it leave? What pulls down? The electrons right here come down, which kick off the OH to grab the hydrogen. So this is HSO4 minus, leaving you with NO2 plus. So what is the next part? Benzene. Okay, so benzene will make a bond right here. And what's the charge right here? Positive charge. Yeah, I heard you say HSO4 minus grabs the hydrogen, and what does the hydrogen do? Leaves the electrons to form a double bond. Okay, give you a second to finish that. Okay, so now let's do the one with SO3. Okay, what's the first step? Huh? Yeah, find the electrophile. So what happens there? Yeah, one of the oxygens, it doesn't matter which one. Whoa, went a little far. Grab a hydrogen. And what's the next step? Benzene. It's going to make a bond to the sulfur, which pushes those the double bond to oxygen up, those electrons. And what's our final step? Yeah, grab the H to reform benzene. Everybody good with those? Okay, then we also looked at directors. There were ortho-para directors. Ortho-para are those activating or deactivating? Activating. And how can you tell if something is an ortho-para director? So the atom connected to benzene, is it connected to something more or less electronegative? Less. And what's the driving force of ortho-para? Stability. And there's also meta-directors, and let's see. Are those activating or deactivating? Deactivating. And the atom directly coming off benzene, is it connected to something more or less electronegative? More electronegative. We can also call them, if we wanted to, electron donating and electron withdrawing groups. Which one do you think would donate electron density into the ring? So the activators or deactivators? Activators. Anytime you donate electron density into something like that, you're activating, you're making it more reactive. Because electrons, when we do these mechanisms like this, we're moving electrons around. So anytime you put more electron density into something, you're increasing its reactivity. So activators or ortho-para directors are sometimes called electron donating groups. So then meta-directors are called electron withdrawing groups. Meaning they're going to take electron density away from benzene, making it less reactive. Which group is a ortho-para director but a deactivator? Halogens. How can I tell if something is a pi donor versus a sigma donor? First of all, what is a pi donor? What does it do? It creates the double bond to take that positive charge out of the ring. And which ones do that? The what? Yeah, but which ortho-para? They're, yeah, the activators. But which activators? They're the ones that lone pairs. So pretty much everything but carbon. So oxygens and nitrogens are usually what we're seeing. So the atom directly coming off benzene Usually you're going to see that as an oxygen or a nitrogen. So the one in our lab we saw that was a pi donor, which makes you extremely reactive. In the lab was the phenol, which would be alcohol. Alcohol has those lone pairs, so it can donate that electron density in there. Okay, so let's learn, before we do more examples with that, let's learn the last kind of two things you can put on benzene. Both of these are carbon groups. Okay, so it's called Friedel-Crafts reaction, because that's Friedel-Crafts. Let me spell that. Friedel-Crafts. Friedel-Crafts. Alkylation. What is an alkyl group? A what? Single bond what? Carbon. So they're just single bond carbon groups. So we're putting just the carbon chain on there. That's what alkylation. Friedel-Crafts, those are just the two scientists who discovered. So of course, if you discover something, you have to name it after yourself, right? So now it's known as Friedel-Crafts alkylation. This is how it works. So let's just do like a methyl. So what carbon group do you think we're putting on here? The CH3. And this could be any carbon group. This is just the one I chose. The biggest limitation of this reaction is if I have a director on there, this reaction will not go if you have a deactivator. This reaction is not a very strong reaction. It'll go if you have an activator or if you just have benzene, it'll work. Okay? But if you have a deactivator, a metadirector, like NO2, this reaction will not go at all. Okay? Which will bring up the next reaction of how can you do it then? So the mechanism for this now, based on other mechanisms you've seen in this chapter, what do you think happens here? The chlorine will attack the Cl. Okay, so at this point we just have our benzene reaction. And what happens here? Yeah, it's going to grab the methyl, causing all of this to leave. And what's the final step? Yeah, this is going to grab the hydrogen off to reform benzene. So not too bad. Now again, the biggest limitation of this is that if you have a meta director, deactivator, this reaction will not work. So Friedel-Crafts, of course, again, both of them, came up with an alternative. So this is their original one, the alkylation, just putting on a carbon group. So then they did this. And it won't make sense at first how this is a good alternative, but it will in a minute. Let's say I want to do this. Let's do this. Can you write it down? See if you can figure out what group will go on benzene. So what do you think you put on benzene? Huh? Not just CH3. With the carbonyl. Yeah. So we would have this. C double bond O, CH3. You see where the chlorine's at? Everything to the other side of the chlorine will go on your benzene. So this whole thing there. And what attaches to benzene is, do you see how the carbonyl is attached to chlorine? Not the methyl. So it's the carbonyl that's attached to benzene. I know. So benzene replaces chlorine, essentially. So let's look at this mechanism. It's basically the same exact mechanism. What do you think happens here? Chlorine is going to attack the aluminum. And then what's next? Benzene. And where does it make a bond? Carbonyl carbon. And you can, if you want to, show this coming up and down, leaving group leaving. And final step? Yes, take off the hydrogen, reform benzene. So you see, I don't think this chapter is too bad. At least I hope you don't think it's that bad. You're always starting with benzene pretty much, and it's decently obvious which reaction you're doing. You can tell the difference between putting SO3H on there and putting NO2 on there, just based on what's on the arrow. Now this doesn't just put a carbon group on there, that puts on a carbonyl, okay? So if that's what you want to do, that's great. But what if you just wanted a carbon group on there? Let's say we have a deactivator on there, okay? I put it on there, meta, and I want to make this into a carbon group because the other reaction wouldn't work. So if I redraw this, this is what it would turn it into, and see if you can figure out what you put in there. look at the difference between the two. Are the carbon number, is the carbon number the same? Yeah? What does this have that one doesn't? Yeah, the carbonyl, the oxygen. And what does this one gain? Hydrogen. So what do I do there? A reducing agent. A lithium aluminum hydride will work. So that's how you can always put a carbon group on there. It takes the extra step, but it's not limited to activators, deactivators, or anything. It can work in any conditions because it's a strong enough reaction. And if you wanted to just put methyl on there, you would have started with the aldehyde. Which reduces it. Basically, take off your oxygen. How many bonds to oxygen? 2. And that's how many hydrogens you add. Okay, so it has already how many? 1. So if I add 2, that would be CH3. Now, like this, either way, let's just look at this one. Would fit as written, is this a meta director or an ortho para director? I've heard both. So 50-50 chance. Meta. Is carbon connected to something more electronegative? Yes. So this is a meta director. Now let's look at this one. What is this? Ortho para. So you could see, let me show you something like this. Let me think about this for a minute. Okay, think how you could make that. Okay, so what do you think here? Yeah, the carbonyl first. How do we do that? And what carbonyl are we putting on there? Yeah, C double bond O, CH3, Cl with AlCl3. So basically, if you need to put the carbonyl on there, the carbon connected to the benzene, that's your carbonyl carbon. That's in there. Okay, then what do I do? Then add the chlorine. And my final step, lithium aluminum hydride. So let's think about why we did it this way. This is the only correct way to do it. So why did you decide to put this one first? They what? Yeah, because these two were meta, the relationship between the two. So I need a meta director. And what type of director is chlorine? Yeah, that one's ortho-para. And then, well, this one's not. This is ortho-para currently, but we can put it on there as a meta. So this ends up being your director. So we put it on there as a carbonyl, and this is our meta director. Now, why did we put chlorine on there first before we reduced it? Yeah, because then it would have gone ortho-para and not meta. So we need to keep this as a meta director. So you put chlorine on first. Then you reduce this to make your carbon group. So the driving force between all of this is how are they aligned initially? So let's look at a few. What if you have more than one director on there? Okay, so what you end up doing is you'll find your, or let's think about this, if I just tell you. What makes benzene more reactive? Which type of director? Ortho-para or meta? Ortho-para because they're called activators, right? They activate the ring. So that is going to be your strongest branch, if you want, okay? So you have, and then you want to find your strongest activator. So what's stronger, a sigma donor or a pi donor? Pi donor, so basically like an oxygen or a nitrogen. So if we look at these, we have methyl, and we have the nitro group. Which one is more activating? CH3, because this is, what type of director is this? Ortho-para. What type of director is this? Meta. So this is a deactivator. This is the activator. So this is your strongest activator between the two. And where does it like to direct? Ortho and para. Can I put something on para? No, because there's something already there. So it's going to go to one of the ortho positions. And what am I trying to put on there? NO2. So do you see in the final product there, I have NO2 ortho. Now you could have drawn it over there, that doesn't matter. Okay? Either position is correct, but you see it's in the ortho position. So let me put another one. I'm going to draw one. All right, look at this one. Is there one of these branches that are stronger than the other? No, they're both methyl. What type of directors are these? Orthopara. So we have to, let's look at this branch first, and I'm going to mark in red, orthopara positions to this one. So I have ortho and para compared to that one, right? Now let's look at this one. Ortho would be these two, right? And then para would be that one. So do you see they actually complement each other? But look at all the positions. Now there is one position that is less likely than the others. Which one do you think that is? One of the top ones. The one on the right. Why the one on the right? It's between two groups there. So it's more crowding. So this is the less likely position. So either one of these would be fine. And what does this put on there? NO2. So for your final answer, I'm just going to put over here is NO2. You could have put the NO2 there, or you could have put the NO2 right there. Let's look at this one. So which one will be the dominating branch? OCH3 is the strongest activator. And so let's mark then all of the ortho-para positions. So ortho would be here, here, and para would be there. Now which position is the worst position? The one in between the two. Now these you have to actually show both products. Up here I didn't. Do you see that both branches are are CH3? So it didn't matter if I put it next to that CH3 or that CH3. There's no preference. It's the same product actually. But here, do you see that OCH3 and NO2? Those are different. So you have to actually draw both of them. And what does this put on there? Br. So Br plus Br right there. All right, so when you get those down, let's take a break. All right. These here, I want to actually eliminate from the list. You don't use them very often, and they're very different from the other reactions, so I know this will make you sad, but we'll just not do them. I know. So the nucleophilic aromatic substitution. And the benzene reaction. Okay, so that only leads a few reactions at the end of this chapter. These do not have mechanisms. These are just a predict the product. So this one here, do you see I have benzene? Now, if we just ignore all this for right now, but you see I have 3 H2. So how many hydrogens does that give me? 6. So I'm adding 6 hydrogen. Where do you think those go? Every single double bond position, which is every position on benzene. So basically this takes away all of your double bonds. It turns benzene into cyclohexane. Good question. Probably just because you can. That's usually scientists, a lot of times their mind is just curious, like, can I do that? And then they get really excited when you can. So, yes, you can make benzene turn to cyclohexane. And you see here 1,000 psi, so you don't have to memorize that number, but just know it's at a high pressure and 100 degrees Celsius, which would be a high temperature. So high pressure, high temperature, because this is actually a pretty hard reaction to do. Benzene does not want to turn into something else. So high pressure, high temperature, and then ruthenium there is your catalyst. And you can put palladium, because usually when we saw this reaction, we take away a double bond, we had like hydrogen with palladium. And you can use palladium as a catalyst, the PD, if you prefer that one, or if you want to use ruthenium. So, no, it doesn't have to maintain the pressure or the temperature. That's why they were excited. So there are, you bring it up, but there are actually quite a few reactions which are reversible, like easily reversible. Okay. The next one is a side chain oxidation. This is one of the ones that was in your lab 5 at the end, using KMNO4. KMNO4 can be used as an oxidizing agent. Do you see that it has a lot of oxygens there? And where we did this before, this is the bad surgeon. So what does it do? Cleaves. And it'll turn your hydrogens into OH, right? Now what this is on benzene is it cleaves everything off after the first carbon there. It doesn't matter how long that chain is. This chain could be 40 carbons long. It doesn't matter. It'll chop the whole entire thing off, except the first carbon, and turns that carbon into a carboxylic acid. And so do you see that it oxidized it? It added oxygens, right? So it cleaved and oxidized, which is what KMNO4 does. So you can put any crazy chain on there. That doesn't matter. Don't let that distract you. Whatever chain you want, you react that with KMNO4, erase it, and just put carboxylic acid. Okay? Yes? It'll do it to all 3 of them. Yeah, it's very reactive. Does that make sense what this one does? And I believe there's only one more. The MBS one. MBS, you see you can actually just write it as bromine. MBS is a form of bromine. And basically what this does with the light, it's a radical reaction. And so it's going to put a bromine on the most stable radical position, okay? Which is never on benzene. It's always one carbon off benzene. Because if I had a radical right there, do you see that I can resonate? I can move all these double bonds to stabilize it because of benzene. Anyway, so that's why you will add a bromine, one carbon off benzene. And so on yours, you had a methyl, an ethyl, and a tert-butyl, I believe. The tert-butyl, the one that's like kind of like a cross, that one won't work because that carbon already has 4 bonds to it. So you can't just put a benzene on there. That would be 5. Okay? So then you have methyl and ethyl. So methyl would be a primary carbon, and the ethyl would be a secondary carbon. Which one stabilizes the radical better? Secondary. So it would be that secondary carbon that will support the bromine. Actually, just like this one right here, if you have a choice. And I think, but it won't, a radical reaction will never happen on a double bond because it's very, very unstable to put a radical on a double bond. I mean, extremely unstable. So, but if I put it right here, I can move that double bond there to to stabilize that radical. And I can end up just kind of like when we did earlier with the positive charge, moving those electrons all the way around. I can move that radical all the way around benzene if I put it there. Versus here, it just stays there. You can't actually move anything around, and it's just not going to happen. So it's always off your carbon chain. So we have, what does KMNO4 do? Yeah, so it cuts off your carbon chain, and what does it add there? Carboxylic acid, which does have oxygen. What does 3 hydrogens plus high temperature, high pressure, metal catalyst, what does that do? Takes away all your double bonds. And what happens if I put Br2 or NBS in there? Bromine where? The first carbon off benzene. Now, if there wasn't a carbon group coming off of there, then there would be no reaction. Okay, so if I had, let's say this was a chlorine there or something, it wouldn't go. Huh? That's light. It promotes the radical reaction. That's actually what starts the radical. It's what forms. Remember, back in like chapter 3 or something, you have, remember we had chlorines that would split apart the initiation, and you have to use light to do that. And so that's why you have light here. Yeah, you usually use UV light. And so what that would do is break up the bromines to start the radical reaction. So it's just there for your initiation of the reaction. A methyl will. It's just if you have a ethyl and a methyl on there, it'll prefer to go to the ethyl. Because then they can put it, or not they, but the bromine can go to a secondary carbon versus a primary carbon. But it will go with a methyl. If methyl was the only thing on here, it will attach itself to methyl. All right, I did want to start a little bit of chapter 18. I know. But just the naming. Yeah. Chapter 18 is ketones and aldehydes. What is a ketone? Carbonyl with what on each side? Carbon groups. And what's the aldehyde? Has a hydrogen. So here's my ketone, carbonyl with 2 carbons. Here's my aldehyde. I have at least 1 hydrogen coming off the carbonyl. Now all I want to do is just go over the naming. Or let's look at these really quick. Do these have hydrogen bonding? No. So, but it does have electronegative atoms. So what do you kind of predict about the boiling point? It's higher, but not as high as if it had like hydrogen bonding, right? Okay, so let's look at naming these. Now this is a ketone, so that it will end in -one. Now what you do is you find the longest continuous chain, which would be what in this case? Yeah, 1, 2, 3, 4, 4, which is butane. But with the ketone in there, we call that butone. Now where is the ketone? Where's the carbonyl? Carbon 2. So I have 2-butone. And then what's this? 3-methyl. So 3-methyl to butanone. So just drop the E. Okay. Now we haven't learned how to do this yet, but let's ignore that for now. Well, I guess, well, it's pretty much the same name up until that point. So you have 2-butanone, 3-methyl. Now how, do you see this is an alcohol here? A ketone is a higher priority than an alcohol. So it'll still end in -one. How you name an alcohol is oxy. If it's a branch, or sorry, hydroxy. You know it's a branch anytime a alcohol is in a ketone or an aldehyde. It is a lower priority, so it'll always be a branch. So ketones and aldehydes are the only two functional groups that we've looked at that would be a higher priority than alcohol. So then what would I name this part right here? For, not methyl, but hydroxy. So we have hydroxy and we have methyl. Which one would come first? Which one? Hydroxy, alphabetically. That's all we look at. So we have 4-hydroxy, 3-methyl, 2-butanone. Okay, so that's all the naming for ketone. Now we'll just look at aldehyde. So for ketone, you're going to end in -one. You need to tell me where the ketone is located because I don't know if it's, carbon 2, carbon 3, 4. You have to tell me where it's at. And the only other thing that comes up is if you have an alcohol in there, we're going to name that as a hydroxy branch. Okay? What would you name this one? Cyclohexanone. Can you see that this is not benzene? Okay. Benzene will have the double bonds. Cyclohexane will not. So a cyclohexanone. And then what is this? 3-bromo. 3-bromo cyclohexanone. Here's the aldehyde. Now the aldehyde, you actually do not have to tell me where it's at because it's always at an end. Okay, by definition, aldehyde has to be at the end. Why? Because I have the hydrogen coming off of there. That's the only way, because if I put a carbonyl right here, you see that's between 2 carbons, it would be a ketone. So an aldehyde, to be an aldehyde, has to be at the end of a chain. So it's always carbon number 1. And whenever you name these, it's going to end in, let me say this correctly, al. Not all, but al. A-L. Okay? So what is the longest continuous chain here? 5. So pentanal. I'm trying to emphasize it because I know when I get lazy, I just call it pentanal all the time. Pentanal. And where is this? 3, and that's called methyl. 3-methyl pentanal. Now the only other thing that could come up, I know you're thinking, well, what if I have a ketone and aldehyde in there? Okay, an aldehyde is more reactive, and we'll go over why on Monday, but it is more reactive than a ketone. So it has a higher priority. So what would this end in? Al. So let's, and I'll tell you how to name that in a minute. But let's do everything but that. What's the longest chain here? 5 again, so that's pentanal. What's this? 3-methyl. Now how you name a ketone, like a carbonyl in there, is oxo. O-X-O. So what would this be? 4-oxo. 3-methyl 4-oxopentanal. Don't worry about this one because we haven't gone over carboxylic acids yet, so I don't even want to get into that. So our new endings are -one and -al. -one for ketone, -al for aldehyde. And our two new branches are oxo for carbonyl and hydroxy for alcohol. Yeah, I got it. Do you? You're the one tested over it. Okay, so I have your exams. And so it's your choice if you want to stay and look at them or not. And I will just call out your name. Okay. Jessica and Luke. Wait, she left. Kai and Anthony. Nope. Jackie and Nicole. Which one is that? The left? Okay. Yeah, just spin the pages over.